In the last Reality on the Rocks of the series, reality itself meets quantum. And it's all beyond our ken.
I wanted to find out how the universe really is, to discover the secret plans and hidden schemes behind creation. Why is the whole show the way it is? I wanted to see how much about everything you could cram into one head. This one. Quarks, mesons, bosons, muons, leptons, taus. Now, not a lot of people know this, but we live in a quantum universe. Okay. I'd come to this notion through months of research, grappling first with the theory of the entire universe.
Well, no, because you can never get right to the edge, no. The edge in relativity has no real meaning.
I'd had to check out the cosmos for myself, from telescopes in the world's highest places.
So I'm looking right into the beginning of time.
Here I was shown proof that the universe began, and that it's still expanding from the bang, a ball of space-time shaped by gravity. Gravity that made the stars and galaxies. Gravity that formed our universe out of the matter that emerged from the Big Bang. Then I'd been to where they recreate the Big Bang here on Earth, to discover what the universe is made out of. Subatomic particles.
Higgs boson.
These tiny chaps follow weird rules of probability. They don't know where or what they are. See, in the micro world, the only certainty is uncertainty.
We're not talking about one thing being in three places at once or anything, are we?
Oh, yes, we are. Oh, yes, we are.
But then I found these laws say cats can be dead and alive at the same time. This is because all matter is just a form of energy. This blurring of energy and matter leads to the startling conclusion that things can be in several places at once. Physicists call this quantum theory. The leap I had to make was to square the quantum with the universe. You see, there's another theory of the universe, a theory of gravity, known in the trade as Einstein's theory of relativity. And these two theories just don't fit together. So the search is on for a theory that incorporates them both, a theory of quantum gravity. Recently, I'd heard about a particle called the Higgs boson, and it works behind the scenes of the whole show. It gives mass to the stuff in the universe. But who is Higgs?
Oh, really? He's still alive, is he? To be honest, I thought he was a guy years ago. Yeah, this is the right one, is it? Yeah, Higgs of Higgs's bosons, Higgs's field and everything. Is he? Well, he's coming here to Oxford. Well, what's it on?
Higgs was giving a lecture on the search for the theory of everything, this quantum gravity business. So perhaps I'd find out what it is. I was about to discover how to rebuild the entire universe out of its tiniest constituent parts. So I knew it wasn't going to be easy.
The standard model of particle physics, particularly the Glashow-Weinberg-Salam electroweak theory, has its origin in superconductivity theory back in the late 50s, the one which tells you how the magnetic field is
Blimey, this was the ultimate answer. I couldn't understand the first thing.
Glashow, Salam, Weinberg, the Higgs boson is a pair of these things, then its mass should probably be no more than
Needless to say, I came out none the wiser.
Between these rather apparently different kinds of physics is a rather fruitful one.
But I'd come too far to let a bit of maths get in the way. Time I thought Higgs got a grilling, Campbell style.
What is quantum gravity?
Well, quantum gravity is, it appears that if you quantize anything, you have to quantize everything. In other words, you can't pick and choose. So if there are, if there are various kinds of forces and fields around, including gravity, which interact with what you've already described in quantum language, then you must bring in gravity too. Otherwise, you haven't got a final consistent theory.
The thing is, what they've done is they've found all the different forces, the things that hold the bits and pieces of atoms together, the strong force, the weaker force, and all that electromagnetic force, right?
And there's a quantum particle for each of these forces.
Now, they haven't yet found any particle which holds us to the Earth. In fact, the thing that Newton found out, boing, things drop and things go around and all that, the gravity, this is the big bugger. Because nobody can find, what it is. We can't find the graviton. And apparently when we do find the graviton, bang, that'll be the thing. Not that we'll understand everything, but maybe what happened with GUT, what's that called? Great unified theory will be ours.
So if you can get gravity happily into the quantum world, the quantum picture, does that mean that you'll then have the equation that'll explain everything?
In one sense, the answer is yes. I mean, that's what people would be aiming for. Then that might be, because Stephen Hawking once put it, the end of theoretical physics.
Our goal is a complete understanding of the events around us and of our own existence.
So if gravity does come into the quantum picture, and everything follows quantum rules, does that mean everything is in many places at once? Is Campbell a quantum being in a quantum universe? Am I somewhere else as well?
Reality on the rocks. Well, as far as I'm concerned, reality is fine, It seems, fine, I'd no particular bother with any of this. And then came the meeting with David Deutsch. Right. He said, at a choice point in your life, you think, I'll go and see my auntie. No, I'll go to the pub. See? Well, at that moment, another universe is born. There is a universe when you go to your auntie, and there is a universe where you went to the pub.
It sounds very startling when you hear it at first, but I think I might be able to persuade you. Well, yes, but I might be able to persuade you that you already believe in this theory in another way. Hello.
David Deutsch?
Yeah.
Campbell.
Right, come in.
Thank you.
You believe that the past happened. You believe that when you came in a few minutes ago, we actually did pass through that doorway and we did begin talking. Those are perfectly real physical events, we think. We're used to there being a parallelism of different times. That is, we have the present of which we are directly aware, and we have the past and the future of which we're only indirectly aware. Well, all that quantum theory is saying is that there are a whole lot more of those of which we're even less directly aware. But we can infer their existence through a combination of theory and experiment.
Is there a name for all these universes?
Some people call it the multiverse.
The multiverse. And the multiverse means all of them?
That's right.
Yeah.
All of them considered as an interacting whole.
Right.
And they all exist at once, both the parallel ones and the past and future ones. The theory of parallel universes is usually used to describe the interaction of very similar universes, ones which differ in perhaps the position of one photon or one electron. And it's those ones that we're really very sure exist. The classic experiment is an interference experiment where one shines a beam of light through some slits or something and sees a pattern.
I had this funny feeling I'd been here before.
The proof of this, or what's led scientists to get on top of this concept, is what's called the twin slit experiment. Now, what happens with the twin slit experiment? Just imagine one slit first, all right? We'll fire light at the one slit, right? The light will go through that one slit, okay? And we'll narrow it down to just one whatever they call package of light, a photon. Like one photon, doing, it goes through that slit. One photon. Okay, now we're going to have two slits. yeah? And we fire our one photon, doing, and it's gone through both. I see, yeah, David, are you sure it was only one photon anyway? Yes, we're certain. and I've no chance it sort of bounced back at all, is there? No. No, it didn't. Right, so what happened there is your little chaps, your little tiny chaps, your quarks and such, inhabit all the universes of the multiverse. Like that. And that is where you have had interference with another universe.
The theory...
I was saying they're physical.
Absolutely, as physical as the centre
this
of the
one.
sun. Yeah.
And it's sort of so that one is identical to this one, except there's one little thing there instead of there.
That's right.
And where are they physically located?
There you're really asking, where are they in our universe? But they aren't in our universe.
Well, I never said they were in it. No, they must be... Well, they're either in it or next to it or somewhere away.
Yes, they don't... When you ask where something is located, you mean what is its spatial position?
Yes.
Where is it in space? But if you ask where is the universe, well, that isn't in space. It isn't anywhere in that sense. It just exists. And similarly, the parallel universes also just exist. Ask yourself...
Well, it just seems to be a bit lacking in the middle of what you're saying there, to me.
I
have no difficulty with saying, well, the universe is that. I mean, it apparently is...
But you do have that difficulty if you think about the past. Where is the past? Well, wherever that is...
Well, I had thought that it had gone, but I mean, with what you're saying, maybe it
That's
it
certainly not the picture that modern physics gives us, because all the universes, the past, the present, and the future, and the parallel ones, are all part of a unified whole. And there is no one of those which is distinguished as objectively the one which exists, while the others don't
know, these
exist.
guys who reckon that they've lived before, you know, like under hypnosis and sometimes without it, it turns out that they were a 14th century nun and...
There's no basis for that in physics.
Pardon?
There's no basis for that in physics.
It seems to be what you're saying, though. I mean, why not? I mean, maybe I wasn't a nun then, but maybe I am now, in as much as I've managed to...
Well, let's keep our feet on the
link with
ground.
that.
I mean, just because quantum theory is weird doesn't mean that everything that's weird is true. It's only the few weird things that quantum theory says are true which are true.
As I understand it, there's a universe for every decision point. You know, like if I'm coming along a road and I either go right or left, there's another universe for when I go right and another universe for when I go
That's
left.
right.
So,
Yes.
so that's going to start another universe.
It's not just the things that you do, it's the things that every atom or subatomic particle does as well.
Right, I see. So there's a separate universe to the number of every atom or subatomic particle.
Perhaps it's better to say one for every possible history of the universe.
All sounded quite unlikely to me, except when, and I never said this, but on the other hand, I had a little thought which you know, might have been something similar. I don't know if it happened to anyone else here, but sometimes I'd have thought, yeah, well, I think I'll go down the pub, but I'll just have a couple of pints. And then, you know, that's all right. I just want to have a little thought, go down there, have a couple of pints, and that's all I've had, right? And I come back, and I've got mystery bruises, right? I mean, 2 pints, I come back, I've got mystery bruises, right? Obviously what's happened in another universe, I went down there and fell into bad company at 8 or 9, and I fell over like that. You see, I had multiverse interference. I just like to.
If this quantum theory of everything is right, then there's more of everything than I'd ever bargained for. A whole multiverse of parallel realities.
As I say, I was at pains to say, I mean, I was doing my best to follow this stuff,
I found it unhandleable, really. But anyway, what I knew was that I would be meeting the great Roger Penrose next. Now, Roger Penrose had been tutor to David Deutsch. And, but then there'd come a point, I think at Multiverse time, when they split paths. Deutsch had gone his way and older Penrose was somewhere else. Anyway, Deutsch, who knew I was going to see his old tutor, Penrose, he said, do it, but he said, just ask him this. He said, if we take on board the observations of quantum mechanics, we cannot avoid the multiverse. Just ask him that. Yeah, I don't understand it with quantum mechanics, quantum gravity and so forth. Insist that there are many universes. In fact, a phenomenal amount of universes.
I think what you have to understand is that in quantum mechanics, quantum mechanics is usually concerned with very small things, atoms, molecules, and that sort of thing. And the rules which apply there do insist that all alternative possibilities must in some sense coexist. Now the trouble comes when you extrapolate that up to the level of people or what have you.
Yeah.
And the thing is that...
Is there any reason why things can't work one way at such a tiny level and a different way up at our level?
Well, I think, you see, that's exactly what I think. Yes, that's right. Yes.
Right.
But you see, if you really take quantum mechanics seriously, if you really think it through, you are really driven to a many worlds view. Yes. So that all these alternative universes do have to coexist, and you're driven that way. But there's no good evidence that the theory does hold right up to that level.
Really? No. No good evidence?
Well, you see, my own view is that there's something missing in the theory.
We're in a state of dither.
It would mean you'd have to bring something else in, and that's kind of disturbing because it needs a new theory. Yeah. But I think you do need a new theory.
Now this was refreshing. When it comes to the multiverse, even the big boys can't agree. Penrose reckons our only hope for common sense lies with good old-fashioned gravity. He's not at all convinced that gravity will play by the quantum rules.
Okay, if you want a unified picture of the world as a whole, then you would expect quantum mechanics and gravity to come together. Now, there are many people who work on these ideas, and there's no theory yet. I mean, there's no successful theory of quantum gravity. But there are many good ideas that people have. But see, one thing I think is important here is that there's no good reason to believe that the quantum gravity theory, whatever it is that unifies those two, will be quantum theory as we understand quantum theory. I think it will change quantum theory. You see, you were asking me before about at what level do things become classical, and that's where
so your view is that if they find the quantum theory of gravity, then we probably won't need all the many worlds.
Exactly. No, exactly. That's right. I certainly think that. Yes.
David, hello, sorry, it's me again. Listen, this multiverse...
Campbell's cosmic consciousness was full of enough balmy ideas. The last thing I needed was someone adding to the problem unnecessarily. It was time for David Deutsch to explain himself.
David, isn't it easier to believe in one universe that's got some weird rules than all these other universes that have comprehensible rules?
I think it rather depends on what you want from science, what you want it to tell you about reality. After all, in a way, the multiverse is one universe with weird rules. The rules say that there are many copies of us. But the weirdness in the conventional way of looking at quantum mechanics is not so much weirdness, it's just that something that doesn't make sense. So, if the question is, isn't it better to believe in one universe that doesn't make sense, or lots of universes that do make sense? Well, then the answer is more obvious.
To convince me of this, David demonstrated how the old view of quantum mechanics, the one that's been around since the 30s, tells us things that are actually weirder than a multiverse.
According to the usual view, it talks about indeterminacy.
So the same as uncertainty?
Uncertainty, the uncertainty principle. What that top card is uncertain until we look at it. That's the usual view.
Yeah.
There is nothing on the blank.
Can I just check? You are saying that the card is uncertain. It's not that we're uncertain.
Yes, according to that interpretation, it's both we and the card who are uncertain. There is nothing on that top card definite until we look at it. When we turn it over, it then becomes definite.
But David, how does the thing make up its mind just as you turn it? The card's still dithering. Look, it's still dithering, David. It's still dithering. Oh, it's made up its mind.
But don't blame me for that interpretation.
Oh, okay.
In fact, one of the pioneers of quantum theory used to say, it's not permitted to ask what that top card is.
Did you used to think that?
Yeah, I did. I mean, when I was a student, that's what we learned. In fact, that's what most...
What? You found it easy to take it on board?
Not at all. It's just... I think when you learn these things, you learn, like Niels Bohr said, you learn not to ask certain questions.
Albert Einstein and Niels Bohr, the founders of quantum theory, argued for years over what quantum uncertainty could mean. Bohr thought it meant that reality is just the sum of our observations. Einstein said, but the universe really is out there. Quantum theory must be wrong. God does not play dice.
Don't tell God what to do.
Einstein could never accept his own quantum theory. 2 years after his death, the new explanation of uncertainty came along. And it wasn't that reality wasn't real, it was that every reality is real. I wondered what Herr Albert would have made of parallel worlds.
Now, in many worlds view, it may be hard to believe, but at least it makes sense. The many worlds interpretation is normal physics applied to a very unfamiliar universe. So really, if we were looking at this pack from a God's eye view, we'd see lots of different packs. And when I take the card off the top, there's a copy of me doing that in each universe.
Yeah, listen, what worries me about this idea is it seems to me that you've thrown away free will, you've thrown away freedom of choice, and all you've left us with is ignorance. You've left us merely with an ignorance as to which universe we're in. I mean, if I do a really good deed in this one, you know, and it makes everyone really happy, so that's very nice. But it's a bit selfish, really, because it's condemning my clone or sister, brother being in the. I suppose I'm a girl in one of the universes. It's condemning them to unhappiness.
I think that's the wrong way of thinking about it.
And I mean, also because well, I think I'll be the lazy one, you know.
Yeah,
well, I'll be the one who stays in bed.
You see, if we were having this discussion and we thought that classical physics was true, then you could say free will doesn't make sense.
David told me I was still holding out for a classical universe where everything ran like clockwork, where the fate of the world was predetermined from the very first tick. In this universe, I wouldn't have any choice at all. I'd be a prisoner of the clockwork. Only by leaping into the quantum world could I rediscover my freedom of choice. But the choice was ridiculous. Either there was no reality, or every reality, a multiverse. Presumably in one of these other universes there was a Campbell lookalike who didn't think this multiverse idea was a looniverse. Anyway, I ferreted out another quantum gravity chap, Julian Barber, and he reckoned he could break down my monoversal insistence.
The world of possibilities is just vast. I don't think we comprehend how many possibilities there are. And I suppose the most amazing thing about quantum mechanics, it says, in principle, everything is possible. Everything, in principle, could be experienced.
So am I right, Julian, that with this excellent multiverse concept, that every particle, every quark, squark, lepton, slepton, muon, tau, each one branches off and has its own universe, but also every instant of time, is yet another universe.
Well, yes. The way I would like to get you to think about this is to ask, what do you mean by an instant of time? Well, I would say that an instant of time is if you could freeze the world and take a snapshot of it, and it would show all the objects in the universe in some particular position.
Yes.
You would have a complete snapshot of the entire universe. Now think about, as you look about this room here, in fact, if you stop and look at everything, the portraits on the wall, the family photographs, me, and even here, look, I've even got my progress book, which I fished out here. Look, you see, even here, here's what seems to be.
You.
Now, you're looking at this progress book at mine, and you're looking at me at the same time. Now imagine a snapshot is taken.
This is sweet.
And imagine a snapshot is taken of this and me and the whole room all at once.
Yeah.
And it's frozen there, and you've got that all frozen in one snapshot. Now, doesn't that tell a fantastic story? That snapshot is completely static, but it reeks of time. If you sat and looked at that snapshot long enough, you would start saying, this is a record of a history of a young chap who grew up and became this crazy fellow Julian Barber sitting here telling you about the many worlds. And there seem to be lots of records, and it all sort of matches, and it matches with your memory when we first met. Even the atoms of our brain are, so to speak, representing all that structure there, so that you can get your notion of time, I believe, from the fact that we are in such a structured configuration whenever we experience anything. So I don't think there is any time at all. All that it is we're constantly experiencing things which seem to tell a very rich story. And one of the challenges of quantum gravity will be to explain why it should be that we do experience that.
I really just fall out of this at a point, because you say, well, there isn't time. There's just these but that is time. I don't see where the discovery is. This is a way of saying what time is, not saying how there isn't it.
Yes, that's true. I mean, let me remind you what St. Augustine said. If nobody asks me what time is, I know perfectly well what it is. But if they ask me, then I'm at a loss. I can't actually put my finger on time. So what I've been trying to do is try and get a clear idea of what do you mean by time. You see, Newton thought that time existed externally. There was a time flowing. As we're talking here, in addition, time is flowing. In fact, let me read you what Newton said. Here's his famous Principia. Absolute true and mathematical time, of itself and from its own nature, flows equably without relation to anything external. So, in Newton's view, there is sort of some God's clock which is ticking away, if you like, outside this room where we can't see. And each of the instants that we experience here is embedded in this external time, occurs at a definite place in external time. Absolute time, as he called it. Now, I think that's quite wrong, because I'm saying that time must be something concrete, something that we experience in this world and deduce from what we can see in this world. So I say the instant is not in time, time is in the instant.
Time is in the instant.
Yeah, well, look, you can see it here. How could you say there was time if you didn't see the evidence all around you? There's the appearance of time here. Look, you see it everywhere you look, the gravestones, the church. This seems to tell a story. As you're here, you see it in this instant now. It's here. But time is in the instant.
But so there isn't ever going to be time travel then?
Well, not in the sense perhaps that you mean it, because the instant of time is defined by what you find around you. That's what it is. So you can't go back and bring in some new material. So if you go back, it isn't the same instant of time, as it were. It's going to be a different one. But you...
The way Julian explained it all seems so reasonable. In the multiverse, time is not an issue, because time is not real, just a pile of snapshots. A world without time. Shame about the time travel, though.
It might be a bit like that. In principle, it's possible. It could happen.
more I thought about it, the more I got concerned about this time travel business. You see, a few years back, I'd run a science fiction theatre in Liverpool, and I'd built a life around time travel, believing that it would be a fact one day. Had I been selling my audiences duff scripts?
Wait a minute. You!
Me?
Yeah, you. Now, suppose you go back in time, you meet your grandfather, and you kill your grandfather. Well, then there'll be no you to go back in time.
It's just a film.
Just a film? It's as real to me as yours is to you.
What do you mean?
Right. Now, your time is a series of instants, right? Okay. Think of those instances as a frame. The first frame is the Big Bang. The last frame is where you are now.
Yeah, but film time only happens when you're watching it.
Au contraire. Film time is in the film all the time, whether you're watching it or not. The time is contained within the images on the unprojected frames. Your time is in frames too, only you call your frames instants. And you believe your future and past exist, don't you?
Yeah.
Well, they do.
Hold on, your future is fixed. Mine is uncertain.
That's another way of saying in your Universal movie, there's a number of possible endings. Now, in my movie, I don't know what's going to come next. In the director's cut, there could be a totally different ending. In the movie version, it might be really exciting. In the TV version, not so good. In yours, there's a number of ways the film can be cut, like in mine.
But if we say that this is a film in a multiverse, who's the director?
You got me, buddy. Let's hope it ain't Michael Winner.
You all right?
It was then I found this article in the Scientific American, and guess who it was by? David Deutsch. Time travel, he said, was possible, but only with the multiverse. That way, you see, you avoid the grandfather paradox, because you travel to a parallel universe, another possible past.
And there was only one. There was only one.
Mr. Campbell, this is your 10-minute call. Mr. Campbell, your 10-minute call. Thank you.
Tell you what I mean. I mean, actually, every instance that there actually was And every instance that there actually will be.
Well, now, if you...
It's like you who's bringing in these probable ones to
well, the difficulty
confound
is,
me.
Well, I agree, and I'm very sorry that I have to do it. And I do incline, like David Deutsch, to think that they've got to be all there, although it's very hard to imagine. But
so Julian, you don't think in any terms of beginning and end, then, do you?
There's...
I mean, do you subscribe to this Big Bang concept?
Well, let me take this model here. I would say that the Big Bang did not occur in the past. It is just somewhere else in this structure here, which I call the relative configuration space of the world. This is the space of all possible configurations. If you take each possible configuration of the universe, which is one of these points here, that could be, so to speak, a possible world or a possible instant. Now think what ordinary classical physics was like. It's very odd. Here's this great huge sea of possibilities.
Yes.
But according to classical physics, only a tiny, miserable little part of it is explored. The actual universe is just this one unique curve running through it. But then it's very strange that all these other huge sea of possibilities, and they're vast, all these possibilities, are completely unused. Now, quantum mechanics, in a way, seems to be much more reassuring, because quantum mechanics is, as it were, picking up all of these possibilities, and in some senses, it's seeing which of them it likes best, which one it's going to give the biggest probability to. It's like a sort of a competition in eternity. Each possible instant here is sort of competing with all the other ones to see which is the most probable.
I mean, to me, the probability is in the future.
But you see, there's no time in this picture. It turns out that time disappears completely. It's a timeless world. You just have probabilities for these configurations. And somehow or other, there isn't anything like it.
Destroy the history of the world?
It does, yes.
I didn't realise this. You seem to be saying that this probability thing is on history too. You say, well, probably the Romans came. You know, we found a helmet. We found this helmet.
For a start, yes. I mean, in the most extreme form, the quantum theory, you have to ask yourself, did I even come into this room? Was that experienced? Or is it just your memory? Remember, you really have to practice Cartesian doubt. Descartes said, the only thing of which I'm absolutely sure is that I think. Cogito ergo sum. I'm aware now. So in fact, quantum mechanics really confronts you with this Cartesian problem, because all we know for certain is that the present instant exists.
My brain was crammed with quantum uncertainty. If I was to catch this time connection, I had to hold on tight to another train of thought.
Einstein's train, where each instant of time is not a when, but a where. We do not move through space and time, but just exist in a greater scheme called space-time. Einstein proved this from the single fact that the speed of light is always the same, no matter where you are or what you're doing. He realized that if someone struck a match in the middle of a carriage, they would see the light from it hit the front and back of the carriage at the same time. But if you were on a platform watching the match being struck, by the time light moves from the match to the ends of the carriage, the train has moved. So you would see that light hit the back before the front. You disagree over when things happen. So even time is only meaningful relative to your position in space. Einstein said what happens when you move is that your time must slow down, and if it were possible to travel at the speed of light, time would grind to a complete halt. Now, in the universe there are objects of such huge mass that they do strange things with light. This is the clue to the secret of everything. These are black holes. Objects of such concentrated mass, even light cannot escape them. So, inside a black hole, light must come to a halt, and this could only happen if time stops. A black hole is the place in the universe where the end of time exists, where reality gets crushed out of existence by gravitational energy. It's the mirror image of creation!
So I'd actually made it. from Big Bang to black holes, apparently in no time at all. This history of time was even briefer than I thought. But surely time can't be an illusion, can it?
Is time real? Or is it an illusion? It's real, isn't it? It's real. It's as real. It's as real. Surely time is as real as you are, Professor.
Well, you're talking about our experience of time, the flow of time. That if you think about the universe and it having originated at a certain moment, in a sense, then you might ask, what happened before, or what was time like at the Big Bang, and so on. Well, that is a situation where you really do have to worry about how quantum theory and space-time structure relate to each other. And it's a big unsolved problem. Nobody knows how to do that. I mean, there are various different ideas people have. And, for example, Stephen Hawking has an approach to this where he talks about imaginary time. He has a scheme in which imaginary time, in this sense, is brought in, and space and time look the same as each other. But it's a particular approach to looking at quantum gravity which gives a picture of what the Big Bang might be like.
I haven't got what is imaginary time. So imaginary time isn't the time before time began.
No. It's
some other
it's often
thing.
a right angle, so to speak. See, time before time began would be minus time. You see.
Yeah.
Whereas this is not negative time. It's square root of -1 times time. It's square root of negative time. That doesn't make any sense.
The square root of negative time.
Well, no. It's like in quantum mechanics. You see, you have to do this.
They'd have to have given him that job.
See, in quantum mechanics, the deeper you look into the way the world works, the more mathematical you find that it is. I mean, and things like these imaginary numbers, in a sense, they're just sitting there in the world. You can't see them in the ordinary way, but they underlie the very precise way in which the world behaves. So that, yes, the laws are governed, the world is governed by incredibly precise mathematics. And mathematics of not always the most obvious kind. It's kind of subtle mathematics. But that seems to be the case. Yes.
So God worked it out mathematically first.
Well, that's a way of putting it, if you like. Yes. I mean, I certainly have the view that the mathematics is there in a sense. It's out there, and the world conforms to it. So it's not that we come up with these funny ideas. We come across the funny ideas. They're there. They're, if you like, God's ideas already. They're out there in the world. So yes, that is a way. Yeah, I would agree with that way of putting it.
I suppose God didn't say, "Let there be light." He said, "Time, gentlemen, please."
Time's an illusion. Blimey, it's 6:30. It was then I got the letter. Stephen Hawking had agreed to see me, but only if I could make it on a Wednesday. I'd got together questions as ultimate as the Campbell brain could muster. Must ask him about that.
It was for me very difficult to know that in a very few minutes I'd be meeting Stephen Hawking, the greatest brain possibly in the world. Certainly in Britain, one would think. Stephen Hawking.
The first of the big questions. Is quantum physics just maths, or is it the way the world really is?
I don't think it has any meaning to ask what the universe really is. Reality is not something you can test with litmus paper. All you can ask for is a model of the universe that predicts the results of observation. Quantum theory does that very successfully. It is a picture of the universe that is often at odds with common sense. But so much the worse for common sense. common sense tells us that the sun goes round the Earth. But Newton's theory of gravity, which says that the Earth goes round the sun, allows us to put satellites in orbit and send men to the moon.
So, for the big man of everything, common sense doesn't matter. I next asked him, could quantum gravity explain everything?
Gravity interacts with everything in the universe. So a theory of quantum gravity would be a theory of everything.
Gravity would be everything. Hey, hold on, just because gravity interacts with everything, it doesn't mean gravity would actually be everything. Or does it?
At the beginning, the universe contained nothing. However, as it expanded, it borrowed energy from the gravitational field to create matter. As any economist would have predicted, the result of this borrowing was inflation. The universe expanded and borrowed at an ever-increasing rate. Fortunately, the debt of gravitational energy will not have to be repaid until the end of the universe.
So gravity is everything. Strange.
It is said that there is no such thing as a free lunch, but the universe is pretty close.
So, if you found the theory of everything, is that going to be all up then for physics?
If we found a theory of everything, it would be an end of the first chapter. But there would still be a long way to go before we understand the consequences and the reasons behind the theory.
I see. All right. Because I had a notion actually that was secretly you'd found it, but we're sitting on it because you weren't really trained for anything else.
No.
Would the theory of everything tell us why we're here?
A theory of everything, by itself, would not tell us why we are here, or why the universe bothers to exist. But it might give us a clue. Finding a theory of everything won't help us to feed more people. It won't even enable us to make a better washing powder. But man does not live by bread alone. Nor does he exist to wash his clothes whiter than white. Surely, the quest to understand the universe and the laws that govern it is worth a bit of effort and expense.
Yeah. Incidentally, I've got a theory that they put dirt into washing powder, because I was washing some... I mean, they weren't really dirty, these trousers at all, but I was washing them by hand, and it was incredible, the dirt that came out of them. I think they put dirt in...
Maybe.
I said to him afterwards, it's all right, that voice they've given you. Stephen, I called him Stephen. It's funny, isn't it, calling him the greatest brain in the universe, Stephen. anyway, that's how it was. Stephen, I said, it's quite nice, that voice they've given. It's all right. So I said, because it's got a sense of humour in it. You see? Yeah. And he went, yes. I said, except when you say yes. I said, I think you should get them to give you an ironic yes. You know? Maybe. Anyway, in any event, what was I doing there? I said, listen, all these trillions of universes of the multiverse, are they as real as this one seems to be to me?
Yes. According to Feynman's idea, every possible history of Ken is equal real. It is just that some histories are more probable.
My past was catching up with me. Or did it ever happen at all? What was I to believe? Nothing or everything?
You see, in science, there is no final truth. There's no final truth. We know things at a given level.
The only reality left to suppose was the multiverse. And that is the story of how Ken Campbell came to be a many universes man.
This is the penultimate answer to what question I can't recall. This is a type out of the answers only. He said, the human race is just a chemical scum on a moderate-sized planet, orbiting around a very average star
in the outer suburb of one among 100 billion galaxies. We are so insignificant that I can't believe the whole universe exists for our benefit. That would be like saying that you would disappear if I close my eyes.
Well, that was the last programme in the series, but if it's left you with questions you'd like answered, why not call the Science Line? It's open for the next 2 hours and every weekday afternoon between 1 o'clock and 7 o'clock. The number's 0345 600 444. And that's also the number to ring for a copy of the booklet that accompanies this series, priced at £3.